Yep, thank you so much. Yep, Doc. Doc, are you still there? Doc, can you hear me?
Hello, Marvin. Yeah.
All right, so yep, we'll start our presentation. So we have lots of attendees today, Doc. As you can see, we have I believe these attendees are from all around the world. So we would
Yeah.
like to officially welcome everyone here for today's webinar. So with me today is Dr. Dipali. She will be our presenter for today. All right, so just few reminders before we start. So for those who are attendees who are encountering issues with our issues in logging in. So just make sure to download the Microsoft Teams so that you'll be able to, easy access on the webinar. And yep, if you have any questions about the presentation, please feel free to, post it under the Q&A section on the top right-hand corner of your screens. All right. So for our most common Q&As, Doctor, this is actually the most questions that I receive every time we have our presentations. So a copy of slides or video recordings will be provided to you for those who have registered to our webinar today. So this will be sent to them in the next 2 business days. All right. So just make sure that
Yeah.
you have registered. All right. And since this is actually a technical webinar, we will be providing a free digital certificate for those live attendees. So just make sure to stay tuned until the end of the presentation of the webinar because instructions will be provided to you on how to claim your digital certificates. All right. Thank you so much. And yeah, Doc, I believe not everyone here has attended our I believe there are first timers here. So I would like to introduce EIT to them just to give them an information about EIT. So EIT is actually an education provider based in Australia. All right, so we have our campus in Perth, Western Australia. We also have our campus in Melbourne, in Victoria, and we just recently opened our Brisbane campus, Doc, which is good news because we have just opened that one. And EIT is an education provider. We are an RTO. We are an higher education institute, and we're also a and of course an education provider and RTO. All right. So EIT is actually dedicated to ensure that our students receive a world-class education and gain experience. I mean skills that can be easily implemented in our workflows. So basically, we offer education that is really needed. They can actually gain skills and knowledge that is really needed in the industry as of today. All right. And then we call ourselves as engineering specialists because we specialize. One of the institutes that specializes in engineering. All right, so we have a wide range of programs from our professional certificate courses, which are short courses, good for professional development or upskilling. We also have our advanced diplomas. We also have our undergraduate certificates, bachelor's degree, graduate certificates and diplomas, masters, and Doctor of Engineering courses. Okay, these programs are actually industry-oriented programs, which are designed, of course, by industry experts to ensure that our students again gain the skills and knowledge that can be implemented in the workforce. Okay, and then these programs remains current in the rapidly changing technology and industry developments, so which is very good. So once you study with EIT, you'll be able to use that knowledge and skills on the workflows immediately. All right. So these programs and our higher education programs are registered under the Australian government. And at the same time, we also have programs that are recognized under the three international engineering accords, namely Sydney, Dublin, and Washington. All right. And these programs are actually delivered by industry experienced lecturers like Dr. Dipali here. Of course, she'll be introducing herself later on. And yep, this people like Dr. Dipali has been in the field for quite some time, and they have been teaching what is really there in the industry, all right? Not just by book, but what is really there in the industry and that you can actually use it, all right? And these programs that we have are being delivered in a unique delivery model, such as like this, live webinars. And then we also have an international pool of expert lecturers and then dedicated learning support officers, and something that we are proud of, state-of-the-art hands-on workshops, remote laboratories, and simulation softwares. All right. So if you want to explore more about EIT, just kindly visit us in our campus, or if you have, you can visit our website and then chat with us, and we'd be happy to, of course, assist you with any inquiries that you may have. So now I will not take this without further ado. Let's proceed to the topics. So today's topic is basics of programmable logic controllers. Okay. This will be delivered again by Dr. Dipali Shinde. All right. She's actually one of our lecturers and course coordinator here at EIT. And yep, I will allow her to introduce herself more. And yep, Doctor, the floor is yours. Thank you.
Thank you. Thank you so much, Marvin. So I would like to take a control now. Is it okay to you?
Sure, Doc. Sure, of
Yeah.
course.
Yeah. Yeah. All good. So, hello and welcome you all in today's webinar. So I'm Dr. Dipali Shende and I'm based in Perth, Australia. I have like my research interests include industrial automation, process modeling and simulation, then autonomous underwater vehicle and process instrumentation and control. And I'm specialized in industrial automation. Actually, I had a chance to see engineering in different perspectives, like as an engineer, as a professor, as a learner, as a researcher, and currently as a faculty and course coordinator of industrial automation in Engineering Institute of Technology. So already Marvin has given a little bit introduction, so I will not go like in detail over here. So we'll start our today's topic of webinar. So in today's webinar, we are going to see the PLC historical background and development. As our topic is like introduction of PLC. So we are going to see throughout this webinar about the PLC and the basics of PLC. So first we'll see the history of PLC, then introduction to PLC, structure and key components of PLC, working of PLC, then different PLC programming languages we are going to see, then some demos and examples we are going to see over here, and lastly we'll have a question answer session and the conclusion. So before starting to the first topic, I would like to ask all of you that how many of you saw PLC and for which application? Can you just drop here in chat box so that I will get an idea? Like, yeah, I will repeat the question. How many of you have saw the PLC and for which application? Where you have seen the PLC? Are you able to write in chat box? Because I'm not able to see any answer. Okay, Ellen Bradley and Siemens. Good. Who else? Okay, yeah, right. Ambra. Yeah, Siemens, Ellen Bradley, and all. Oh, that's great. Honeywell. That's great. Mr. Bushi. Yeah, Ellen Bradley. Oh, so many. Yeah. So thank you so much for your reply. So here, first we will see the background of PLC. Why PLC came in the market? Okay, what was the purpose of that? So PLC, actually, what is PLC? PLC means it's a programmable logic controller. So it is a digital computer. You can see it's a simple computer, and that is used for automation of industrial processes. So industrial processes means, for example, control of machinery on factory assembly lines. So we have a different industries, like we have a steel industry, then we will have a fertilizer industry, then automotive industry. So there, that industry has a different control processes over there, and for to control that processes, we need a PLC over it. So PLC is used as a controller. So it is a simple digital computer. But before the advent of PLCs, this that relay-based logic was in the market. So industrial control system was relied on relay-based logic. So these systems was using the electromechanical relays to create a logic circuits, which were used to control a machinery, and um, that was like it was like wired up for to complete the or to fulfill the particular application. It gets wired up, and data was sending from the one device to the another, and it was operating and it was controlling the devices. But that relay logic systems were very bulky, complex, and difficult to modify, so making them inefficient for increasingly complex industrial processes. That's why now PLC came in the market. But the main purpose, to come in the market, is like previously the General Motor was looking for their production line, automotive production line. They were looking for the alternative for the relay system. So in 1968, so Dick Morley has developed the first PLC. Just give me a minute. I will stop these notifications. It's already not there. That's fine. Okay, so here, because of General Motors, actually Dick Morley has developed the first PLC, and it is first ever PLC has introduced in 1969. So that PLC was the Modicon PLC. So very first ever PLC in the market was the Modicon PLC for General Motors. So Modicon stands for the Modular Digital Controller. So this innovation was marked the beginning of the new era in the industrial automation. So instead of the relay circuit, now they started to use the PLC for control purpose. PLC rapidly, because of this, their flexibility and ease of programming and their ability to be programmed without changing the physical wirings, this PLC rapidly gained the popularity in the market. So this is the little bit history about the PLC. So PLC is used for the different processes, like in different industries like petroleum, steel, automotive industries. So you will able to see the picture of these industries, and it has three parts. Normally, it's an input, CPU, and output. Now, again, I will simplify what is PLC means what. For example, by taking the example, like we have an electric motor and we have a button. So by pressing this push button, we wanted to run this electric motor. So in that case, what happened? We will, like for PLC, we will have an input, CPU, and output, these three parts. Okay, so we'll connect this push button to the input side and electric motor to the output side of this. We'll do the programming on our digital computer over here. Okay, PLC programming, and we'll download that programming in the CPU. So that will process. Now, when we'll push the button, now our task is like, when we'll push the button, it should on our electric motor. When we'll again it push, we are pushing it again, then it, in that case, it should off the electric motor. Now, in first case, what will happen when we'll push the button? In that case, some electric signal, okay, will go to the input device over here. Okay, that but that electric signal will not be processed by CPU as it is. So that need to convert into some language which is understanding by the CPU. So that electrical signal will be in terms of 101010. Okay, then it will get processed over here. Already we have downloaded programming on the CPU by by using the logic, different languages of PLC. After that, again, this signal will go to the output. Okay, and output, again, that signal will be converted into the electric signal again instead of 101010, and this motor will on. Likewise, again, if we press the button over here, then our motor will get off. So this is the simple logic. So how PLC works. So it's like this. So this is the simple example of what is PLC. So now here, this, are you able to see my screen properly?
Yes, Doc, I can see your screen.
Okay, because I can see the small part only. That's why I was asking. Okay, that's fine. So this is the PLC in industry. So here we will have a PLC rack in the industry. Okay, so on rack, we will have different inputs, outputs, processors, then communication modules will be there and power supplies will be there. So basically, signals will come from the field, right? So there will be one field that will be our input over here. Okay, so here there will be a PLC. So we will have a PLC rack, and after that there will be an operating station. There will be a control room, you can say. So in control room, we will have a operator station or engineering station in that case. So here, operator station, what it will do, it will operate something. Engineering station will design, okay, design that thing. And here on PLC rack, we will have a different modules, IO modules, you can say. IO modules will be analog or digital. So we will have a digital input, analog input, digital output, analog output, likewise. So we will have different IOs. Communication. So for this module will be for communication protocols. To get the signals from the different field devices, we need some communication protocol like Ethernet, Profibus, or Profinet, like this. So field devices will be, what will be the field devices? Okay, suppose on field, in plant, we wanted to measure a temperature. So there will be a temperature sensor. Control valve will be there. That means some sensors, transducers will be placed over there. So sensors will send the signal to the PLC rack, and then it will process the signal. Okay, and as per the input, it will take the action to control. For example, suppose we wanted to control the we wanted to on and off the control wall of the plants. So what will happen according to the flow? Okay, suppose there is we will have a maximum flow than our set point, then that wall should be off. If we have a low flow, fluid flow, then our set point, in that case, that wall should be on. So likewise, okay, so that signal will go to the PLC, then it will, by using the PLC language, it will execute that. Okay, it will use the logic to develop the programming, it will execute, and as per the this output of this, it will take the action. Okay, action on that particular device. So it works like that. So one by one, in next slides, we are going to see in more detail. So in that on the plant, it looks like this. Okay, so we will have some field devices, we will have a control room. In control room, we will have some operating stations, then engineering stations over there, and PLC rack will be there. So PLC has a different IOs. So it is a digital input, IO means input and output. So input, it can be a digital or it can be a analog. So digital inputs, analog inputs, digital outputs, and analog outputs. So what is digital inputs? That is also called in short DIs. So these inputs receive discrete signals that are either on or off, that is 0 or 1. Okay, such as signals from the push buttons or switches. So that will be on and off, like your uh, remote control of your TV. So that normally by using that, we on and off the TV. So that signal will be 0 and 1. So the signals from push buttons or switches will be 0 or 1 in that case. So that is the digital inputs for this. Digital outputs means what? DOs, these outputs send discrete signal to control devices like relays, lamps, or solenoid valves. That means by it will require what? Digital output 0 or 1 to on and off these lamps or relays or solenoid valves. Analog inputs means AI. So these inputs receive continuous signals from the field devices. So like few sensors which are measuring the temperature, pressure, or flow. So these are the continuous signals we are getting from the field. So that signals can vary what like in the range between 4 to 20 milliampere or 0 to 10 volts. So that are the analog inputs. And so that are converted into a digital values that the PLC can process. So we need to convert that values as well. So that are the analog inputs. Analog output means the output side, the continuous signals from the field devices we will get, that will be the analog outputs. So these outputs send continuous signal to field devices such as actuator or variable frequency drives or control to control processes based on PLC's instructions. So it will based on the PLC when it execute the program, then it will based on that PLC's instructions, it will take a action. Okay, it will control the process. That valve will be on or off, like actuator will be position of actuator will be vary. So that is the analog outputs over here. Now in market we have a special IOs as well. Okay, so special IOs means what? Actually, special IOs means this is used for a special applications like when our standard IOs are not capable to do the function properly. It is beyond their limit. In that case, special IOs are used over here. For example, high-speed controllers. So for high-speed controllers, now there will be the more counts. Okay, more pulses will be there, and high-speed pulses will be measured by using the like we are measuring the frequency. Okay, so here how high counted pulses, high speed pulses, sorry, high speed counters. So for that purpose, normally special IOs are used over here. And there are so many examples where we can use this special IOs, and that is designed for a complex operations over here, and that handles the complex task, you can say. So this is the good example and the pictures of the digital input. So you will see over here, there are the different digital inputs, limit switches and sensors are there. It looks like this: liquid float switch, then push buttons, selector switch. Okay, so different switches and sensors are there. So these are the pictures, like how it looks like, and these are the digital outputs. So there are different types of digital outputs like relays, overload relays, power contactors, then indicator lights, auxiliary contactors. So these are the different digital outputs. Now how it gets connected, interfaced, you can say, or connected or integrated. So you can say see here digital IOs and PLC. So digital input and digital output. So digital input means we will have a limit switches or relay contactors. So push buttons and switches will be there. Okay, when it will be like, suppose this is normally open basically. So when it is closed, in that case, it will create a contact over here, and according to that, relay solenoid balls or some output devices will operated, and in between we will have a PLC rack for execution purpose. Okay, over here, and that is required a 24-volt DC signal. So in this PLC rack, we will have what power supply, different modules, DIDO model. As we are talking about the digital IOs, and over here, that's why we have a digital input modules and digital output models, and processor, CPU, power supply will be there. So this is input DI and this is output. So how it is integrated, it is shown over here. Then we use the analog IOs also in the industry. So analog sensors like ultrasonic liquid level sensor. This is the few examples which are analog IOs we can use. Then temperature sensor, then process pipe rotary valves. So here for analog IOs, analog inputs and outputs, analog inputs will be oven temperature, fluid pressure. These are the few examples of AI and few examples of AO, analog output. So AIR, oven temperature, fluid pressure, fluid flow rate outputs, and outputs are fluid wall position, okay, control, motor position, then motor velocity. So these are the AOs. These are the examples of the AOs and special function IOs. So we will have like counters, high speed counters, RTD, special type RTD, thermocouples, pulse stretchers. Okay, so for this, we can use the special function for like particular task or for complex tasks. We will use the special function IOs. As an input side, we will use this, and as output side, we will use stepper motor, servo motor, and AC output. So understand special function IOs means what? Like, remember the example of like pulse stretchers or high speed counters. So where standard IOs has beyond their capacities. Now they cannot handle this special task. So in that case, we can use the special function IOs. In next PP slide also, we will see in detail about this as well. So another part of PLC is what? CPU. Okay, processor. So CPU, central processing unit. So this is the processor. So the normally it is a microprocessor based system, this processor, and this processor includes but not limited to what will it will have reading the status of the field inputs. Okay, then running the control program across these fresh inputs. Running means it will execute the program. Writing results to the field outputs. Okay. Then housekeeping, including firing of task, event, etc. Communication protocols. It will include tasks that can include assisting in reading or writing IO across racks. Then alarm, acknowledgement, etc. Then updating values to and from the SCADA, supervisory control and data acquisition system. So updating the values on the SCADA, then HMI is also a part of this, that is human machine interface, then databases. So all these will be included in the control process while execution your program. Okay, so we need to know the like status of the input and execute, and then it will take action or results for the field outputs. Okay, so it will include SCADA and HMI as well. Okay, so for monitoring analysis purpose, we need a SCADA over there, and human machine interface. So some display unit will be there to display the values. So this is the one part of CPU. Okay, input then CPU. Now moving ahead, programming device. So previously, actually programming device was a dedicated and expensive device used for the PLC. But nowadays we can program this. PLC can be programmed from office or on your PC or via the network anywhere. So we don't need any programming device separately over here. We can do on our PC as well. So here there is a one you can say one terminology, that is the scan cycle. So PLC scan cycle, that is very important. Okay, the PLC scan cycle means what? So the time taken by the PLC to complete a one cycle is called the PLC scan cycle. So complete one cycle means what? So that means one cycle will be what? First, it will read the inputs, because there are three parts, right? Input, your CPU programming part, and your output. So it will read the input first from the input devices. Then it will execute the program. So logic will get developed by the user. Okay. Then that logic will, as per the inputs that, sorry, the logic will get executed. Okay, and for that purpose inputs will be used over here, and as per the this PLC instructions, out it will take a action. So adjacent outputs will be there. Okay, so here it will take the action. So this full cycle, the time taken by the PLC to complete the one cycle, is the scan time of that PLC. Okay, so this is the scan cycle. The scan is a continuous and sequential process over here. So that is the main difference between the PLC and DCS. Actually, PLC has a faster scan cycle. So whenever we need fast operations, okay, so in that case we normally use the PLC. And also the one another main difference for between the PLC and DCS is like IOs. Okay, scalability, you can say. That means if a DCS can have a thousand of IOs, but the PLC has a few thousand of IOs only. And normally, suppose we are talking about in market, if IOs are below 1,000. So in that case, we use the PLC, and more than 1,000, then we normally use the DCS. Like it's like orally we can say about the PLC and DCS. So this is this diagram shows the PLC main and IO memory system, like RAM, output tables, programming memory, in tables, CPU. We will have input modules, output modules placed on that. Okay, then communication modules will be there. Okay, now if there is a wireless communication, so we will have a network, right? So for wireless communication, so sensors, actuators. So input side sensors will get the data from like field devices, you can say, and output models, there will be the actuator. So this is the representation of like PLC. Now there are different types of PLC in the market. So these types are mainly small compact PLC, modular PLC, and expansion rack type PLC. So the compact PLC means all this you can say input program, this is designed all in one unit with CPU, power supply, and the modules will be in one unit only. So it will be compact and it will be used for the small applications. Okay, and where like we don't have a much space to place the PLC. So for in that purpose, this small compact PLC we can use. Another one is the modular one. So here in this picture, you will able to see that modular one is like it will have a racks, different modules we will have. Sorry, different modules in a rack we will have, and it also has capacity to place the extra module as well over here. So that is the modular one. So this will be used for the like uh, small applications to a medium size applications. You can say this modular is used, and expansion rack type will have uh, like um, you can say we can do the expansion in future, like expansion modules. We can place more slots over here for expansion purpose over here. So that is the expansion rack type. So module over here. So these are the basic PLC types, but PLC can be classified according to the number of inputs and outputs, cost, their physical size as well. So as per the number of IOs, it is classified as nano and micro. So nano means it has the smallest size with 10 to 16 IOs. 10 to 16 inputs and outputs. If it has, it is called the nano. So number of IOs are 10 to 16. In micro, with up to 32 IOs are there. Also, it is classified as per size as well. So compact size, rack mounted size. Okay, over here. So that rack mounted is also called the network PLC. So compact size of PLC has up to 960 IOs over there, and rack mounted or network PLC has a several thousand of IOs over. So on plant, if we are talking about a big plant, so normally we use the rack mounted PLC over there. So in picture you can see racks are like this. Okay, so it will have a different slots. If you have seen the PLC, you will understand that different modules we can place over here. Okay, so this is rack type. As per cost, also it is classified. So as per cost, it is the low cost, mid range, high end PLCs over there. So normally rack mounted PLCs are called the high end PLCs because it has a high performance as well as it has the high cost, as well as it has the expansion capability as well. So that is the high end PLC. So in on the plant, we normally use the high end PLCs. Then low cost PLC, so it is micro PLCs or nano PLCs are used over here. Micro and nano means number of IOs are small, that is 10 to 16 or 32 IOs we can use. So that PLCs are the low cost. Then mid-range PLCs, that is compact and modular PLC. These are the mid-range PLCs in the market. Now we'll move ahead and we'll see the different languages of PLC. Like we need to do the program in PLC. So for that purpose, we need to use the different languages or one language of PLC, but in market, we have a different languages of PLC over here. So I have a question for all of you. How many PLC languages you know? Yes. Okay, can you just list out, like instead of writing 4 or 5 languages? Yes, LD you know, ladder logic, sequence chart. Okay. One is saying Boolean, ladder, structure stack. Okay, function, data blocks, instruction list. Yeah, that's great. Many of you know about this, right? So at least basic of this, many of you know. Okay, fine. So we'll move ahead of our PLC programming languages. So we have a graphical and text-based language. So in graphical, so ladder logic comes in the graphical. Okay, so ladder logic, functional block diagram, that is FBD, and sequential function chart, that is SFC. Okay, it is called SFC. And text-based language is structure test, that is ST, and another is the instruction list, IL. Okay, because as we are writing in terms of the text, that's why this language, like it is comes under the text-based language, and graphical, like we are going to see how we can develop a ladder, okay, and how we write the ladder logic, FBD and all this. So these are the graphical languages. So we have around 5 languages over here. Now in industry, it uses normally a ladder logic and some part of the ST, you can say. So yeah, this mostly they are using these languages, but SFC, ST, IL, FBD are equally important. And for what purpose where we will use the SFC, where we will use the ST and IL and FBD. So we are going to see on this PPT. So currently uses LD as a norm, ladder diagram as a norm, and very small part of ST for maths. Okay. So here SFC. SFC is more ideal for sequential or recipe based or batching system. So like for designing the process and then fleshing it out with algorithm. So written in written in LD for typical logical circuit. So SFC is used for the batch processing normally for recipe or sequential as sequential flow chart. So where we will use the sequence over here. So sequential flowchart language, this language will get used over here. ST is for mathematical and database work. Okay, structure test. Then IL, instruction list, only used for optimizing parts of code that needs to be optimal. Okay, instructions. So part of the code that needs to be optimal, in that case, we will use the IL. So example of this we are going to see. Okay, in next PPTs. And FBD is ideal for highly repetitive patterns. Okay, functional block diagram. So it will be easy to do the programming or coding in that language when there is a repetitive patterns of coding with the same functional blocks. So function blocks can be written in any language in that case. So if there is the same function block repeatedly, we can use, and FBD will be easy to use over there. So likewise, these are the different languages we can use while developing a PLC program. Now, first we'll see the ladder diagram. So here you can compare, like this is the relay diagram and this is the ladder diagram. So in relay diagram, normally we like put the switches like this, switches, relay. That means we normally put the symbols of that. Okay, so start, stop. So will be like this. Okay, over here. And we should know like what is this vertical lines and what is called for this horizontal lines. So vertical lines are the power rails, you can say, and the horizontal lines are the rungs. This is called the rungs. Okay, power rails, and these are the rungs. So these are the individual circuits over here. So this ladder logic changed. It is bring to electrician for the day into the eras of PLC can be immediately productive over there. So in ladder logic, normally we use like normally open, normally close, like this symbol. So I think in next year on next PPT we have this. So each rung will have like each rung must start with at least one input and one output should be there. Okay, it must end with the one output. So that is the basic funda while developing the ladder logic LD. So here, start, stop. So there are many electrical devices. So we normally show like this. So for switch, like normally open switch. So we show like this. This is normally open switch. This is normally closed. So this is the parenthesis, and there is one slash over here. So that is the what normally closed switch is over there. Then there is normally off, normally on, then set, reset will be shown like this. Okay, so this is the these normal conditions are shown like this in ladder logic. Now, okay, we'll see like normally closed switch. What does it mean? Well, we'll take one example only instead of taking all the examples. Suppose normally close. If we are taking normally close switch over here. So in that case, what happened? Normally close means, for example, I wanted to run my electric motor continuously. Okay, so in that case, my switch will be like, it will be normally closed. But when it gets activated, then it will become a normally open. That means when I push the button off, in that case, my motor should off. So in that case, what happened? When I push the button, in that case, electric circuit breaks down, okay, and motor will be off. So this is the example like this. So fail to safe, you can say normally closed switch will be the fail to safe condition. So these are the conventions of ladder diagram. So this is some examples. So if you wanted to like use the same output somewhere, so we can use the same name or same labeling to over here, like start, stop, run. So we are using the run button here. So device can appear in more than one rung of a ladder. So example, if an output's value is needed as an input elsewhere, use the same letters or numbers, okay, to label the device in each situation. So that is the basic concept, like we should use the same number so that it will understand that we are using this output as a input here. Now, this is the various IO notations in ladder diagram. So as we know, we have a different PLCs. Different companies has developed these PLCs, like Mitsubishi PLC, we have Siemens, Allen Bradley, AB. Okay, then we have a telemechanic PLC. So all these have the various IO notations in ladder. So here you will able to see that input, it is showing as X400 or Y430. Here in Siemens, IO dot knots and output will be Q. Like I is input, this is output. Here X is input. X means input side, Y is the output side. So input, output, Q. In Allen Bradley, it's a I and O, input, output for this. Okay. So this indicates like these notations indicates that this is input, this is output, and very first like you can say the first digit after this input is showing that it is the module number, okay, of that device, and second digit it shows it's a channel number. So first, whether it is input or output, that will indicate first you can say the first letter, then very first digit after first letter will show the model number, and after that it will show the channel number. That means on this model this channel will be, because in PLC we will have a like different modules will be placed over here. So we will have some input module over, okay, we will have some output module, okay, AI, AO, DI, DO will be there, okay, some or some communication module will be there over here. So in this case, it will indicate that in on input model will have a different channels. Okay, so it will indicate channel number 0. So input model number 0, channel number 0. So that is for integrating purpose. Okay, so we will have a different notification over there. Now this was all about the like ladder diagram, LD. Now we are going to see about the function block diagram. That is another language, FBD. So here function block diagram. So this is the actually called the high level graphical programming language. So here it will processing elements and signal flow between the elements over here. So in functional block diagram, you can see over here, suppose there is an AND. In example, we'll see in detail what does it mean. So these are the inputs. Suppose these inputs are ending over here. Okay, so then here this is ending another end here, getting the output or like, so symbols, graphical symbols, okay, signal, will actually each graphical symbol or a box has related input and output parameters. So it will be shown by pins, and the assignment of parameters by lines between the pins it is shown. So it will have a graphical symbols or boxes over there in plugged FBD. We will have this thing. So this is similar to the electronic circuit diagram, you can say. So this represent the program functions by means of graphical symbols or boxes. So like electronic circuit, it is connected. Then another one is the instructions list, IL. So these instruction list, it is similar to like this programming language is the assemble language. So assembler language, this instruction list is a programming language that consists of series of low-level instructions, so much like assembler. So each instruction consists of mnemonics code or a new line operator followed by a one or more operands, that is subject of the operator. And here we can store in a memory register all these things. So here you can see, actually I'm not able to see this table. So it will have an instruction like suppose they wanted like in Siemens PLC or they have a some notification, different notification over here. So in Siemens or PLC, we will have a as a notification for this. This is for LD notification for this. Okay, Marvin, can I ask you to zoom this one because I'm not able to zoom this table?
All right, let me just take control of that, Doctor.
Mhm.
Just a sec.
Mhm. Yeah, that's all good now, I think. Yeah. That's fine. Thank you so much.
Can
Okay.
you see it?
So, yeah, that's all good. Thanks.
Okay.
Uh, so this is like, suppose instruction is like we wanted to start a rung, okay, with open contact. So in that case, for open contacts, so in Siemens language, okay, for this instruction list, we will write A for this. And for other like Mitsubishi and all other language, it will show like LD is there. Okay, so that is the instruction list program. So we are giving LD. Then another example we are going to see, suppose we have a closed contact. So for closed contact in CMA, like here, we'll write IL as AN, okay, or LDN for this. That means it will understand that it is the contact is closed already over here. Okay. Likewise, we will give this some instructions over here in this language, IL language. Okay, if I'm taking control, I think it's again goes small. Okay, that's fine. So sequential function chart. So that is the another language. Sequential function chart, we will have like states over there and some transitions over there. So each state will be like represent as a box. Okay, then we will have a horizontal bar over there, that is the transition condition. So that must be made before moving from current to the next. Okay, so in every step there will have a transition condition in between. That means one it gets satisfied, then only it will move from the current to the next state. Likewise, so remember that these two rules in SFC always. So rule one is the steps. So in this, steps can never be directly connected. That means we cannot connect states directly, 1 or 2. Okay. So they must always be separated by a transition. So that is the one rule we need to follow in SFC. Another rule is the transitions. So that is the decisions gates between the states, you can say. Transition means it will get the decision that this condition is satisfied. Now go to the next. So these are the decision gates between the state and can never follow from one to another directly. They must always be separated by a state. So that two rules we should keep in mind always while developing a like this programming in PLC by using this SFC. So here you can see like start, stop is there. So start is the first state, stop is the last state, and there are the steps between this as well. And each these states are different, differ by using the transition condition. So there is a horizontal line that is called the transition condition. So after every step there will be a transition condition in SFC. So like here it is more clear. So initial step, okay. Then there is a S1 up to Sn steps, and in between there are the transitions over there. So this is the functional flow chart. Another is the structure test, that is the ST. So this ST is strongly resembles the old language, that is the Pascal. So it will have a series of statements, and that statements will be separated by this semicolon. So in its name only, structure test, that means we will have a text over there while developing any logic. So like light is equal to switch A. Light will receive state of switch A, that is on or off. Whatever the state will be of switch A, that light will receive. Or light is equal to switch small a, light will receive state of switch A of this, that is on or off in that case. So series of statement is separated by the semicolons, and statement use predefined operators and subroutines to change the variables in this case. And these variables is defined values, internally stored values, or input or output values in that case. Okay, so these are the few examples like how we can use the operators, which are the different operators while using this structure state language. So in structure test, we will have a conditional statements as well. So in that case, how to use that, or how to write when there is a condition. So for example is given there. If now once there is a condition, that means if then else will be there. If then else and endf will be there. So example is like if limit switch 1 and workpiece is present, then gate 1, open the gate 1. Gate 2 will be closed in that case. Else gate 1 will be closed and gate 2 will be open in that case, and end up. So this is the condition. That means if limit switch 1 is present and workpiece is present, open the gate 1 and close the gate 2. Else close the gate 1 and open the gate 2, like this. Another example is very similar to that. If input 1 is equal to 1, then output is equal to 1. That means when input is 1, output is equal to 1. Else output 1 is equal to 0. Now output 1 is equal to 0. That means in that case, input 1 will be 0, right? So output 1 is equal to input 1. So this is identical to this. Output 1 and output 1 and input 1. So remember that be careful of unintended sloppy programming. These two sets of instructions are functionally equivalent. Hence, functional equivalent. Hence, conditional statement is contraindicated. Okay, even though functional equivalent, conditions are different in that case. During these two statements. So these are the example like for ladder diagram. Okay, so instruction list, the FBD. So how these are just to show you like how we normally write this. So this is the good example of LD. Here you can see, okay, IL and FBD. Functional blocks will be there. So examples of the FBD. Now, as we know now, we have a basic idea about like how this we can write a code in different languages in PLC. So here there is a one example. We are going to see like there are 4 sensors. When there is a valid inputs to the sensor, that is activated state, the contacts will open. So are they NO or NC sensors? So that will be normally closed. Normally we use design a system where there is no output when any one or more of the 4 sensors is activated. Otherwise, there is to be an output. Draw logic functional block of the system, okay, FBD, and ladder logic rung of the system. So now there are 4 sensors, 1, 2, 3, 4. Okay. When there is a valid input to the sensor, the contacts open. Okay. So when that will be normally closed, it will open. So one of the input, that means no output when any one of the 4 sensors is activated. Suppose this sensor is this input is activated. In that case, it will become what? Normally open. So in that case, they will not get any output over here, right? So in ladder, we are going to see like, yeah, normally open and normally close, how it works. And in function block, we'll write this like this box. We will write greater than equal to, all are equal, then we will get output. Any one of this is not same, then we'll not get any output over here. So this is also one simple example how we can use this. Now, this is another example, like a single lamp is required to be switched on if a pump is running and the pressure is satisfactory. Okay, so pump is running, that notification for this is X400 and it is normally open, and pressure is satisfactory, X401 normally opens. When both conditions are satisfied, okay, or there is another condition as well, or whenever the lamp test switch, that is X402 normally open, this normally open is closed. So sorry. Whenever the lamp test switch is closed, that means this one, this switch is closed, design the system and draw a ladder logic and logic FBD for this. Now the condition is what? Both the this condition should satisfy, like pump is running and pressure is satisfactory. In that case, just switch on the lamp. Okay. Or when this X402, that is the lamp test switch, this is closed. Okay. In that case, it should be on. So we will write like this. We will draw a ladder like this. For this, normally open, normally close. When both are closed, it will go off. Okay. When it is closed, then it will be on, normally closed. And for FBD, functional block of the system, we will have what? 2 conditions are satisfied. That means we'll put the and over here, pump and pressure, then your lamp will be on. Or okay, or second condition is if your test switch, okay, is closed, in that case it should be on. So we can draw like this. Okay, we can develop diagram like that. Okay, so this is the another example of LD and FBD. Now now more actions. It's presenter view only. Marvin, again, I need your help. Zoom this slide, please. Can you please do this for me? Marvin, are you there? Yeah, thank you so much. Yeah. Because even though it is presenting. Okay, fine. So we'll move ahead. So die stamping process. So this is the good example of SFC. Now we have seen the LD and we have seen about the FBD. So how to like develop in SFC? So this is the one example. We have a die stamping process over here. Okay, so process is like a metal stamping die is fixed to stamping block. Detect workpiece placed by hand. First detect it, then clamp workpiece in a place with electromagnet. First detect, then clamp it in place. Then extend cylinder to stamp die into workpiece. Retract cylinder, then release workpiece to allow removal by hand. Now, main actuators have what? In this case, you can see the down solenoid for piston, for die extension, you can say up solenoid valve. This is the up, okay, up solenoid valve and down solenoid valve over here. Okay, so these are the main actuators: up solenoid valve, down solenoid valve, and gripper for securing workpiece. Like because our one condition is what, that clamp workpiece in place. So we should have a gripper over there, so it will grip the piece. And then sensors are like upper limit, lower limit, and detect new part placed on die, whether there is a like part placed or workpiece is there or not. So detect that. Okay, it's placed on that. So now we need to develop uh, this in a SFC. So here in SFC program, we will have like, we will initialize first, then another one will be like stage. Now there will be a different steps over the step 1, step 2, step 3. Okay, will be there. In that we will like put it our conditions over here. So here first we will initialize the things. Okay, we will have a transition period over transition over here, that is the auto. Okay, so it will detect the line and all. Okay, so then we will have like auto initialize these things. Then we will have like we'll see the weather conditions are satisfied or not. If not, that is not satisfied, that means your this workpiece is not placed, or it has not stamped. Okay, so in that case, again it will go to the step 3. It will stop and again it will initialize, it will start the process again. Otherwise it will go step by step and our like task will get completed. So this is the another example of like this is the example of the SFC. So extend and retract and all these things will happen. It will stamp on workpiece. Okay, so how to write? So just giving the example, because we are not going in detail with the programming part, because this is the introductory webinar only. So I'm giving you just introduction. Maybe we'll plan another webinar in detail of programming and all these things. Okay, next slide, please. So typical programming software functions are like develop PLC program, check program, then simulate that program and download program to the PLC. But with this, we also need to check the status of PLC, whether it is running or not. So online status, running in PLC, CPU or in program mode, etc. Then single step PLC program, or we need to force IO to discover the errors for this. Then diagnostics. So check the status of PLC and IO modules. So diagnose that and then take backups, that is upload of PLC program by downloading to VG unit. So main steps are develop the program in selected programming language, check that program, that means compile for errors, then simulate it. So you will understand the logic errors in that. So remove that errors in that and then download program to the PLC and then run. Okay, so these are the typical programming software functions. Okay, so there are various PLC applications over here. So few applications like in manufacturing industry, PLC can use automotive, food and beverage industry. So here PLC manage packaging, labeling, bottling process in food and beverage. In chemical processing industry, they can monitor and control temperature, pressure, and flow rates as well. In building automation, PLC is used for HVAC systems, lighting, security systems for that purpose. Then power plants, transportation. So for transportation, traffic light control, escalator, and elevator. So these are the very good examples and day-to-day life examples. And we have seen PLC over here. So these are the applications of PLC, and not only these applications, there are lots of industrial and domestic applications where PLC get used in the market. Okay, so these are other applications of PLC. Now here is a one. Yes, please, next slide. Yeah, here actually we wanted to show you one demo, you can say. So in EIT, we are using this PLC trainer kit for education purpose. So we have a production line trainer over here. So this is the automatic and flexible production line trainer kit. And this is the good example of the good example of the production line system, actual production line system placed in the industry. So here on this trainer kit, there are different workstations over here. So student can task a particular workstation, okay, and they can combine this task and they can study the most complex system of the industry in EIT only. So here for education purpose, we are using PLC in EIT. So here you can see few of our students are working on PLC. Yes, next slide. So here this line is like production line is like I will give you a little bit idea about this production line trainer kit. So this is like sorting process. We have a suppose it like we have a different workpieces over here, different color workpieces like black, red, white, and all these workpieces are here. Suppose we have given like we are a right we have wrote the program for like particular like red work pieces we don't need in the system. So in that case it will get sorted, and only black and white one will be passed through this production line. So there is one more trick, like we are placing a small part of work piece inside this big work piece as well. So that is the another process. Okay, so here on this system, it has many robo arms. We have a conveyor. We have many sensors. We are using a Siemens PLC over here, S7-1200 PLC to control this whole process. And this every workstation has a different control over there. That means we have a 7 PLCs over there as well. So that's why we could able to focus on one task, and we can club many tasks together, and we can see the whole system working in this. So here our students used to work. So this is quick demo I wanted to show how it works. I just wanted from here. Okay.
Doc, I think they cannot hear they cannot hear
Okay.
the
So
video.
what?
So yeah, let
Uh,
me just.
okay. I will do one thing. I will share from my side, and quickly I will
Okay.
show the running only, which is what
Mm-hmm.
I will share from my
All
side.
right. Okay, Doc.
Okay.
Thank you.
Just give me a minute. Uh, so I think I'm. Just give me a minute. Okay, let me know. Is it audible? Marvin, is it audible?
Yes, Doc, I can hear it from my
Yeah.
end. So let's ask our attendees. Can you please send us a thumbs up if you will be able to hear the video? Thank you.
Okay. That's great. This is how we are using a PLC for education purpose. Okay, on PLC training trainer kit. So that's all from my side. Thank you all of you for your patience. And I know you are attending this webinar from different parts of the world. So it might be morning, afternoon, or evening for you. So thank you so much for joining. And if you have any question or queries, or if you need any further assistance, then please feel free to reach out. Thank you so much.
Yes, that's true. Please feel free to reach us. We have course advisors here. I'm one of the course advisors as well. So please feel free to, get in touch with us. You can visit our website or send us an email. We'd be happy to, of course, assist you with that. Thank you so much, Dr. Dipali, for that very informative, and I can feel the dedication in doing this presentation. So yeah, good job on that one. Thank you so much. And yep. So yeah, well, the next slide that we have, Doc, is these are the leading brands, right?
Yeah.
Yep, these are the leading brands of PLC. So I believe some of
So,
us here are already familiar with
mhm.
these companies. So yes, Doc.
Yeah, these are the leading brands of PLC. So normally ABB, you might be knowing Fanuc, ABB, Siemens, Mitsubishi, Beckhoff has their PLC, Toshiba, and Schneider Electric. So it is this one is playing a big role in the market, you can say. So yeah, so
Yep, thank
this
you
is
so
all
much,
about
Doc.
PLC. Yeah, yeah.
Yep.
And these
So
are
yeah.
the few references. Actually, a few of diagrams and a few
Mhm,
material I have taken from these books and some websites. So these are the references for this today's webinar.
mhm.
So thank you so much. That's all.
Thank you, Doc. So yeah, we'll have for most common questions, what are the courses that covers this topic? So as you can see on your screen, these are the professional certificate of competency in programmable logic controls. Okay, from the name itself, PLCs and SCADA systems. We also have advanced diploma of robotics and mechatronics engineering, bachelor of science online in industrial automation engineering, and online masters of industrial automation. So for our upcoming webinars, we'd like to announce this one. So for September, we have 3 webinars, September 10th and 17th. So basically, it's about heating, ventilation, and air conditioning profession. I mean, sorry, for the intakes. These are the upcoming intakes. Okay, we have September 10th, 17, and we also have October, as you can see on your screen. All right. So now let's proceed with Doc. We have few questions about the courses. So I have listed some here, although I believe our attendees right now have lots of questions on their minds. So if you have, please share it with us so that we can actually answer that one. All right. So the first one, Doc, is someone said, one of our attendees said, I can see DCS is not really necessary since the PLC can actually be used as decentralized. Please, I need clarification on this.
Okay, so actually, we normally say that PLC, programmable logic controller, if there are a less number of IOs, we can use the PLC. But nowadays, in the market, we have lots of combination. That means we can give the output of the PLC to the DCS as well. And DCS is particularly like it's a distributed control system. So if we have a big plant or we have plants located on the different locations, in that case we need to use the DCS for that, because wirelessly also we are getting, and DCS has actually it has its own redundancy power, you can say. So yeah, so DCS, if we have a we like in plant we have thousands of IOs are there, so in that case we need to use the DCS over there. We cannot use only PLC. So now, yeah, I think
So
I
DCS
answered
is
your
important as
question.
well.
Yeah,
Yeah.
DCS is important as well, because on big plants we can use the DCS, and remotely through RTOs, remote terminal units, we can take the
Hmm.
signals from the field devices, and they have a lots of advantages, you can say. DCS has
All right.
lots of advantages. So yeah.
Thank you so much for that, Doc. So, all right, well, our
Uh,
second question would be, can one program language be converted to another without developing afresh?
oh, without developing a fresh. So I would say we can develop a different language separately. Then we can, like, different languages we can use to control any system over there. But yeah, um, I need to find out some, so because I'm not
Mm-hmm.
sure about any software is there to convert it
Mm,
directly, because now
yep,
most of the companies are developing like separately for
that's
different.
true. All right.
Yeah.
All right. Thank you so much for that, Doc. So,
Hmm.
we have two last questions here. I mean, three last questions, which are very interesting as well. Can you please share the type of software where we can apply the PLC languages explained?
Type of, sorry.
Sorry for that. Can you please share the type of software where we can apply the PLC languages and explain?
Okay, so softwares for different companies has their different software. Like Siemens has like S7, like Siemens has Step 7. I think version 13, V13. So S7 13 we can use. So different companies who has developed PLCs or who has their PLCs has a different softwares for them. So we need to use that software while developing the program.
I see. We have another question here, Doc. What are the major PLC problems we are likely to encounter, and how can we solve the problems?
Major PLC problems in terms of what? That means if this question is not clear, major PLC problems.
So yeah,
Mhm. Can you just write over here again and the question
yeah,
who has asked, or you can just
yeah. Just provide us a detailed questions,
detail?
question,
Yeah, yeah.
yeah, in detail,
Mhm,
so that we can answer that one for
mhm,
you.
mhm.
So the last
Yeah.
one would be, how we connect the DCS to the main PLC in the plant. That's our last question, Doc.
So this is the another webinar I could say, because today's webinar was based on the introduction, because programming, then interfacing of the different devices, like we will have like as I said, through remote terminal units, or through RTUs, or through like we can take the signals from the different devices. We need a communication protocols to communicate or interface that devices to the DCS or PLC, you can say, because today's webinar is for PLC. So I will talk about the PLC. So for that, actually, how to interface, how to connect, how to that that is actually will be another webinar. So I need to
Oh
explain
yeah,
in detail
that
in
is
that
something that
case
you
diagram.
guys need
Yeah,
to watch out.
interfacing.
Yeah, it will be in another webinar. Or if you want, you can
Yeah,
study with us, send your
yeah.
application, and we'll be happy
No,
to
it will
assist you with
take
that.
time actually. Yeah, it
Yep,
will take time. Yeah.
that's true.
So
That's
yeah.
true. Yep.
Mm.
Thank you so much, Doc. That's actually our last question for today. Thank you so much. And then for those who are asking how to get their certificates, here's the instructions. All right. So you need to of course, fill out the survey form, and then basically after 4 business days, they will be able to provide you your certificate. So the form that is on your screen right now, the link and the QR code will expire on the 2nd of September. So just make sure to, do the survey and then scan the code so that you're gonna be able to get your certificates. All right. So that's it. I'll be posting as well the link here. All right. And here, all right. So, okay. So, all right. Thank you so much,
Yeah.
Dr. Dipali. Thank you
Uh,
so much for that. Yep. Yes, Doc.
yeah. Thank you. Thank you so much. And I can see one of attendees saying that already he has taken admission over here. So I wanted to actually add with your previous slide, Marvin. So we have online plus offline, that means on campus industrial automation courses, like Bachelor of Industrial Automation, Master of Industrial Automation, and also we have a DEng program. Okay, doctorate program in our campus, and online also you can do So thank you so much, all of you. Yeah.
Thank you so much, everyone. I think this concludes our webinar today. Again, Doc, thank you so much for that very informative. And of course, I can feel the preparation and everything for this presentation. Thank you so much. And yep, this concludes our day. And have a great day, everyone.
Yeah.
Thank you so
Yeah.
much. Bye for now.
Yeah.
Bye, Doc.
Thank you and have a great day. Bye. Bye.
Bye bye.
Thanks.